I'd like to introduce the co-chair, Michael Lopez Alegria, also the commander of Space Station, and I was there first time. Thank you,
Christopher. Thank you. Good morning, everybody. Welcome back. Welcome especially to all of the students here. This morning's session was very scientifically and technically based. What we're going to talk about is going to be, I hope, not only informative but also entertaining. The picture that you see is, it's been debated whether this is the most iconic photo or the one that Bill Anders took circling the moon, but this is certainly the one with a person in it that is the most evocative. So, this is number 2, Bill. So, we've been doing EVA for 50 years, and the first one was done on March 18th, 1965, and with that as a preamble, I'd like to just ask Alexei Leonov to stand up and greet everybody as the honorary co-chair of this panel. No, So, we're going to hear from Alexei a bit later, but before that, we're going to hear from some real experts in the field. I think EVA is undoubtedly one of the most powerful experiences that anybody has felt. We have had about 550 people travel to space. It is a difficult, dangerous, intense, but beautiful experience flying to space is. Whatever adjectives you use to describe flying to space, you need to multiply them by something to describe what it's like to do an EVA. And about 200 people out of those 550 have been lucky enough to do that. And before you on stage are represented 25 of those EVAs and over 150 hours spacewalking. So it's really a panel of experts. So the rules of engagement are, I'm going to ask each of these 5 panelists to talk about their EVA experience. And I've also asked them to describe, each of them differently, a particular aspect, a particular EVA system, whether it's a spacesuit or a manned maneuvering unit or a future suit, so that we talk about not only where we were 50 years ago, but where we're going into the future. And to start, I'd like to introduce the first speaker, Luca Parmitano, who's a major in the Italian Air Force. He's a test pilot. He is the youngest and best looking of the speakers. He won the Medaglia d'Argento al Valore Aeronautico, which is the silver medal for aeronautical valor after he landed his AMX fighter after a significant bird strike. That was given to him by the president of Italy, not the bird, but the medallion. And he has done 2 EVAs. The reason that he is so young, he's been on the fast track. He was selected for pilot training in 2001, selected to be a test pilot in 2007, selected to be an astronaut in 2009, selected to fly in 2011, and flew his one and only mission in 2013. During that mission, he did 2 EVAs. One was routine, the second one was not, and I hope Luca will tell us about it. Luca Parmitano.
Thank you. I'd like to make a small adjustment to that, the one and only mission so far. So, very slight but important difference. So I have a short video to show, but before we start with that, I'd like to kind of latch on to what is the theme of this conference is inspired by space. Now, all the astronauts here have been inspired by space, so I would like to talk a little bit more to the students, to the people that really are the future of spaceflight. And they are definitely, and I apologize to everybody else, but they're definitely the most important part of the public as far as I'm concerned. Why is human spaceflight so important? I always say that there are 3 parts to it. One is science, second one is technology, and the third one is a component that takes the 2 of them, and it's exploration. The 4th word would be inspiration, but we are already talking about that here. How does EVA relate to those three words, science, technology, and exploration? Well, In general, science and technology really go hand in hand. However, for EVA, you could say there isn't really a lot of science in it right now, in the presence. But we do need the EVAs for science. Dr. Marshburn, Tom, showed you a picture earlier, I don't know if you remember, where there was a panel of material studies that was outside the space station with a person outside in a suit. That person had installed a misse, which is an experiment with all those materials, and another astronaut needed to go back outside to retrieve it and bring it inside. I happen to be one of those astronauts that participated in EVA such though. So science does need EVA. As far as technology goes, well, already the spacesuit, the EMU, of which I'm going to talk about, is a marvel of technology. It really is. It's the evolution of the same suits that were tested by the Apollo astronauts back in the 60s and 70s, and then it evolved into what today is called the EMU, Extravehicular Mobility Unit, and we're not done yet, definitely not done. We are going to evolve even more, and that's going to be your job out there in the second tiers. It's going to be your job to create a better suit, and so technology will create better suits, and that will take you to other places beyond where I will ever go. And just remember, when we think about what it means to do exploration, so we do science, technology, and when we do exploration, we think about a different planet, but curiosity or spirit are not sufficient. We want to see that man leaving the footprint on the red sand, grabbing the sand with the gloves. Those gloves, those boots, that prints, it will be an EVA suit. So that's where exploration and EVA come together. Let's start with the video. And it starts with this interesting image, which is of Chris Cassidy, as soon as we see him. There it is. Chris Cassidy is in the background, and what you're seeing here is it's called a safety tether. For those of you who watch the movie Gravity, the safety tether is to prevent something like gravity from happening. We don't want to get lost in space, but you can take volume down, completely down, yes? And I wanted you to see how much force that safety tether has. It's about 1.5 pounds of force, and the reason why I wanted to show it is because it will become important later on. These are the suits. These are the EMU suit Extra Mobility Unit is a modular unit. They're not personalized. They can be sized to different body types. We have different huts, the hard torso, that can be adjusted to, can be selected so to fit different size of astronauts. But then the only parts that are really personal are the gloves. The gloves, we need dexterity to perform EVAs, to perform really any kind of job. So we try to have personalized gloves so that to make it as comfortable as possible. Now remember that the suit being pressurized is not a hard suit, it's a soft suit. In order to create an atmosphere inside, it has to be pressurized. That pressure is 4.3 psi, which makes it as hard as a tennis ball. Imagine every time we want to grab something using our hands, it's like squeezing a tennis ball. And if you do that for 6.5 hours, 7 hours at a time, it is incredibly fatiguing. Doing an EVA is as tiring as running a marathon. Here you see images of my first EVA. In my first EVA, everything went swimmingly, so to speak. You will get it later, and also for those who didn't laugh. Everything went swimmingly, it was perfect. We were ahead of time. We did a lot of different work, some space station reconfiguration, some science, retrieving panels outside, and also some maintenance where we replaced cameras. This is a picture that I took of Chris Cassidy outside. This is me installing a cover at the very edge of the space station. So basically here I was doing the Titanic scene where I'm in the tip of the boat, of the ship flying. Now, this is the beginning of my second EVA, which went literally swimmingly because I had a little encounter with water. This is an animation that shows a little bit of what happened. I will not go too much into details here. I will leave it hanging so that we can talk about it later. But to put it in a, how can I put this nicely? I had an emergency and I almost died. And the water came from inside the suit. There was a major malfunction, an irreversible mechanical malfunction that started flooding my helmet with water. Because of that, they had to send me back inside. And here you can see the very final moments of the EVA where my colleagues, which you can see from their faces how tense they were. This is about 45 minutes after the EVA was called as a terminate. They came, they recovered me, and what you see flying around, that is water from my head, which was stuck to my head like that. And you can pause it here. So this is a pretty iconic, not as iconic as Bill Anders' pictures or or Bruce's picture, but this water it created an effect which we didn't expect. And it created more problems than we imagined when it was into my helmet. And again, hopefully there will be more time for questions after my esteemed colleague will talk to you about it. Thank you for your attention, and I will pass the word to Oleg.
Thank you, Luke. Thank you, Luca. There will be time, by the way, after each of the presentations, we're going to have a panel discussion that I hope will involve questions from you. So I'm sure somebody will be interested about how it happened and how he got through it. Next, I'd like to introduce Oleg Kotov. He is a lieutenant colonel in the Russian Air Force. Interestingly, he didn't begin his space career as a cosmonaut. He was actually a medical doctor. He started at Star City as first a deputy and then the lead test doctor. He was a flight surgeon. He was an instructor on biomedical training. And then he flew 3 long-duration space flights in 2007, 2010, and his last one he launched almost exactly 2 years ago today. He was commander on 2 of those missions, kind of guy you want to have when things are going wrong, and things did go wrong. On his first mission, during entry, the Soyuz unexpectedly transitioned to ballistic entry. On his second, he had to take manual control of the Progress resupply vehicle as it was doing a supposedly automated rendezvous and docking. He had to take over manually and fly it in the last kilometer. And on his third mission, he did 3 of his 6 spacewalks, including the longest Russian spacewalk ever, 8 hours and 7 minutes, and also took out the Olympic torch. So please, Oleg Kotov.
Yeah. Thank you, Oleg. Thank you for everyone. And, прошу прощения моих коллег, моих соотечественников. Я буду говорить на английском из-за проблем перевода, поэтому прошу прощения еще раз. Okay, dear colleagues and guests, I really want to talk today not only about my specific EVAs, my specific experience in this area. I would like just speak out about some future problem, about our perspective in EVA. What is our goal in future? You know, is NASA and Roscosmos designing new version of spacesuits, but honestly, this is just new modification of old system. We're gonna bring up to station the new Orlan MKS suit in the end this year, maybe in the beginning next year to replace old version of Orlans there. But in general, it's going to be the same suit, the same idea, the same construction, with everything the same. And the same story is happening with NASA spacesuit. But let's talking about the future. What is our goal for EVA? I want to bring my opinion about that. So when we're talking about EVA, we're talking about whole system, including the suit, but mostly this is planning EVA, is a training EVA, supporting, supplying, and all process covered with these words. So let's start with training and planning. You know, our experience is we train each crew individually for perform specific EVA. It's very reliable, very good experience, but this process doesn't give us flexibility in operationally during the flight. If you take a look on the last few years, we had about 4 or 5 unscheduled EVA on the US segment. That means these EVAs hadn't been trained for this specific crew, but performed in with very good quality. That means maybe take a look forward and start training crews only for generic operations, a common operation, just do the standard operation, and after that, during the flight, do specific training on board the station. Do like on-board training. And this is easily to do. If you have general skills, knowledge, and you know how to use a spacesuit and tools, you have a whole set of tools, you are very good to go and perform any EVA. And I think my colleagues think the same way, right? So that's idea about the training. About the planning, again, give crew more rules, more power to plan the EVA by themselves. That's I got from my experience. You know, the ground team always very good to plan a sequence of EVAs, but sometimes they have no idea what's going on station, how it's really easy to do. And we always have discussions up and down, how to do best way, how to create best sequence, how to do that to finish have done this EVA. But again, it's I think as a crew is pretty much good shape to help ground to schedule the EVA in their own way. How to do is better. And about the spacesuit, probably if we take a look on sci-fi movies, we'll see that what's the EVA? Just spaceman just jump in. Yeah, George Clooney, jump in suit, open the hatch, go outside, do the job, come back, close the hatch, get out from the suit. Again, it's the ideal version. And but really could do something in this way. For example, to make the prep and post phases of EVA shorter and easy. You know, it takes about 6-8 hours to get ready for EVA. It means a prep station, airlock, spacesuit, operators to perform some prep activities before EVA, and then finally open the hatch and do tasks. I guess we need to give direction to people, engineering community, to try thinking about to make it shorter. That means a change design of suit, change the procedures, how to perform EVA goals. Again, we can ask a medical community to think any idea how to make short desaturation, maybe change the pressure suit or to work as much shorter way, more efficiently, right? Yeah, so that's my idea. It's my thought about what's our goal is for future EVA's activity aboard, not maybe ISS, but next station, next vehicle, or next generation of flights. So again, I'm ready to discuss these topics with you, so but I've done so. Thank you for your attention and спасибо за внимание.
So, thank you, Oleg. The next speaker is a man whose picture has probably been seen about as many times as the Mona Lisa, perhaps. He's a true Renaissance man, and I say that because he is a certified smart guy, graduated #2 in his class from the Naval Academy, went on to get a graduate degree from Stanford in electrical engineering, obviously one of the most prestigious institutions. But when he was little, he told his parents said, "Mom, when I grow up, I want to be a naval aviator." And she said, "Well, you got to pick one." Come on, guys. And he did. He became a Navy carrier-based fighter pilot, over 5,000 hours, in most of them in tactical jets. He was selected to be an astronaut in 1966. He was the astronaut support crew for Apollo 14, which is sort of the backup to the backup crew. He was a Capcom during Apollo 11. He flew 2 space shuttle missions. On the second one, they deployed the Hubble Space Telescope, setting an altitude record for the space shuttle of 380 nautical miles, which makes him the person who's been farthest from Earth, except for Bill Anders in this room. But he's here to talk mostly about what he did on his first flight, was to do the check flight of the manned maneuvering unit. Bruce.
Thank you, Mike. And let me just address the quote from my parents that you were thinking of, I believe. The theme of this Congress is inspired by space. And of course, when I was growing up, we didn't have astronauts. My inspiration, my heroes, if you will, were the comic strips. Buck Rogers, Flash Gordon, people of this sort. And when I mentioned to my parents that I'd like to fly in space or be like Buck Rogers, the answer was that, well, man may eventually fly in space, but surely not before the year 2000. So why don't you come down to Earth and do something practical, like learn to drive a battleship or something of that sort. And instead of learning to drive a battleship, I elected to go into the Naval Academy and was firmly committed towards nuclear submarines, the first of which, the USS Nautilus, which had come to the Naval Academy on a visit. And I was headed in that direction until one afternoon in October of 1957, we heard that a Sputnik had been launched, and I happened to have a shortwave receiver in my room as a lordly senior or upperclassman, and we dropped a wire out the window of the dormitory 5 stories down into a moat, and actually were able to receive the beep, beep, beep as Sputnik went by. So that was the story that goes with that. But what I'd like to do today is talk a little bit about maneuvering units. They're sort of a personal rocket propulsion system. And I was surprised that immediately after my activities with the MMU, the French came out calling it le fauteuil volant, the flying armchair. And this appeared to hark back to man's first experiment with rocket propulsion, which I am told was conducted by a Chinese emperor early in the first millennium AD. Now, this is not quite so far-fetched as you might believe, since Zvezda in the Soviet Union built a solid propellant maneuvering unit. These are little individual solid rocket motors, a similar array on the back. And when the translation hand controller is operated, it electrically steps through and fires the next solid rocket in sequence. Fortunately, this was never flown in space. However, I will give you some other examples in the U.S. The first spacewalk was by our friend and colleague Alexei Leonov, here depicted on a postage stamp from the Soviet Union. And of course, during the EVA itself, we have some photography. This was in the spring of 1965. It was a time when we were very competitive with the Soviet Union. Mr. Leonov, General Leonov, had about 12 minutes worth of spacewalk. And of course, we in the United States had to top that. So 3 months later, Ed White came out and did twice the spacewalk duration, 23 minutes. So we were thereby back in the game of who's on first, who's on top. I'd like to point out that Ed was using a maneuvering unit called the handheld maneuvering unit, which basically had a couple of small cylinders of gas and a grip, and you could either fire one thruster away from you or two thrusters in a tractor or mode pulling you. And this was an elegant, simple concept that was fiendishly difficult to operate properly. And we spent at least the next 12 years trying to kill off that concept, and it kept coming back from the ashes, somewhat like the phoenix. Our next step along the lines of maneuvering unit was a device built by the United States, under contract to the United States Air Force. This was the so-called astronaut maneuvering unit. It had hot gas thrusters here formed by the decomposition of hydrogen peroxide. And you'll note down here that the subject, in this case Ed Gibbons, who was one of my compatriots who died in an automobile accident, is wearing some stainless steel mesh trousers to prevent him from getting the proverbial hot seat from the hot firing thrusters. This unit was flown on Gemini 9 with Gene Cernan assigned to test it. And I've got to point out to you here, this was the United States' second spacewalk, the first one involving real physical exertion, and the suit was not up to it. The technology was not up to it. So that Gene became very overheated. The visor of his suit became fogged up to the point where he couldn't see out, and it was almost an emergency mode in which Tom Stafford, the commander, canceled the spacewalk, brought him back inside, and that gave maneuvering units in general a bad name. It was about this time that I came on the scene in the summer of '66, and with two other individuals decided to see if we couldn't rehabilitate the concept of maneuvering units. So we proposed an experiment to be flown inside the Skylab workshop about I'm going to say 22 feet, about 3 meters worth of flying space in here. And we also learned a lesson in systems engineering and system development in that the concept prior to a contract award was for a nice svelte maneuvering unit that fit on your back and could be carried through an airlock. As we progressed down through the critical design review, this is what we wound up with. I'm in the suit in all three cases, and I can assure you that being bent over like this was a result of the weight of the unit supporting it. Nonetheless, as a maneuvering unit, it did fly quite successfully. We simulated it in a large 6 degree of freedom moving base simulator where you could go 20 meters this way and about 6 meters side to side and up and down, and a 3-axis gimbal system. This is a cutaway mock-up of a cutaway of the Skylab workshop. And later on in flight, Alan Bean and 4 others flew the actual M509 experiment, if you will, inside the Skylab workshop. And we used that data to proceed towards developing the manned maneuvering unit. I would mention also that, okay, I thought I had a slide in here. There was another device called the foot control maneuvering unit, which tried to build on the thought that your natural balance in a gravitational field could be used for controlling a maneuvering unit. That device was put to rest with the flight of Skylab as well as the handheld maneuvering unit. Our concept for the space shuttle then was a device which was mounted in a flight support station out in the payload bay in vacuum. A crewman, myself and Bob Stewart, would come out of the airlock, get in the foot plate, and remove some launch restraint bolts, service it, check it out, back into it, and I stress there was no connection other than a mechanical latch and a seat belt. There was no electrical connection, no gas connection, anything like that between the pressure suit, whose integrity we wish to preserve, and the manned maneuvering unit. And I would point out also that this was the second successful flight of the United States spacesuit, the extravehicular mobility unit. It had had problems on STS-4, STS-5. Finally was successfully used on STS-6. And when you decode STS-41B, it comes out to be the 10th flight of the space shuttle. Anyway, without further ado, on the fourth day, after 4 days, we came out, went through the routine. I'm over here in the red stripes, Bob Stewart, my partner in crime, so to speak, over here. And we set out and flew the unit very uneventfully. We had put a great deal of effort into testing it. I had been involved in the design, the development of the unit, and as I backed away from Challenger, this was the perspective. This is Bob down here trying to get into a foot restraint on the end of the manipulator arm. And as I got farther away, the only range-finding device that I had was something that NASA called the solid-state rangefinder. And this was a piece of aluminum bar stock, which if you held it out at arm's length, against the length of the payload bay, it had notches that said 100 feet, 200 feet, 300 feet. Anyway, we got there, and I successfully went out about 100 yards, 100 meters, which was the plan, came back in. One of the surprises, though, was that as I got out away from the shuttle, it became very cold, or I became very cold. I was out away from the payload bay, so I wasn't getting any heat reflected back into the pressure suit. And we had a big knob on the front of the pressure suit that said C on one end, a couple of notches, and H on the other. And naively, I thought that H stood for hot, but H just stands for not quite so cold. And the suit was designed to support someone doing honest physical work in a space environment. And flying the manned maneuvering unit was a matter of using your fingertips. So my metabolic load was extremely low and got cold. Since this was early in the program, the heat rejection system, which involved a sublimator, that is a porous plate which had ice formed on the outside, water was fed from the inside to the out, and as it sublimed, it took heat away, and you had a coil of tubing running through it with the water that circulated through the liquid-cooled garment. The ground rule was never turn off the sublimator, because if you try to restart it, it may go and blow all the water out. Well, I got so cold that finally, consulting with Mission Control, he agreed that it was a situation where we had to try it. I switched off the sublimator. About 15 minutes later, I was comfortably warm again, switched on the sublimator, and it started working, no problem. And we had put to rest yet another taboo or bugaboo in the space program. And so far as I know, it has never failed to properly start or restart. But anyway, I'm talking too much. Let me move ahead. You've seen other pictures of the MMU. I am not going to show my, quote, iconic, unquote, image, but I really personally do like this one. This is from a so-called God's eye view, that is a third perspective, someone else with a camera sitting out here or thereabouts. Alexei Leonov was trained as a watercolor artist, and this was for a reason. The fact that there are scenes that you cannot capture with a camera, and this, in my opinion, is one of those. The MMU was used on 2 other space shuttle missions in the servicing of the Solar Maximum mission and the retrieval of 2 satellites later in 1984. Following the Challenger accident, however, NASA opined that they did not have enough money left to recertify it for flight on the new shuttle. And also he had developed a maneuvering technique referred to as low Z that allowed us to drive the shuttle right up to a satellite without the thrusters impinging on it, which reduced the necessity for the manned maneuvering unit. It has subsequently been used as the basis of the design of the SAFER, which, as I'm sure everyone realizes, stands for Simplified Aid for Extravehicular Rescue. That's why we call it SAFER. And this is used on all spacewalks aboard the International Space Station as a sort of life vest or safety belt. In case you come loose from the space station, this allows you to turn around and maneuver back. It is single string, no redundancy, low propulsion capability, about 8 feet per second versus 66, but it could save your life. Now, I would be remiss if I did not acknowledge that the Soviet Union also built a manned maneuvering unit. Here you see Sasha You see Sasha Serebrov, I believe, and Alexander Viktorenko inspecting the Soviet manned maneuvering unit. A different aspect, different picture. I believe this was taken at the Paris Air Show. And then, of course, being flown from the Mir station. Both Serebrov and Viktorenko flew the maneuvering unit successfully in February of 1990. I would point out that they are using a safety tether, and let me explain that in the space shuttle environment, we spent $3 million building a safety tether and then decided not to use it. The reasons we decided not to use it were that in addition to being a hindrance, if it were slack or limp, it would be wrapping around your foot or your leg or the high gain antenna, and if you had to use it to snub your velocity, like the ice skater pulling in his or her arms, you'd be likely to wrap around the orbiter as you reel back in. But we also, in addition to having a totally redundant unit, had the capability for the space shuttle to fly over and pick someone up if there was a double malfunction. The Mir station had no such maneuvering capability as the ISS does not, and both Viktorenko and Serebrov were outside in pressure suits spacewalking at the time, so even if they had had a maneuvering capability, there would have been no capability to actually chase after someone. So for that reason, if I were in the same situation, I would have had a tether as well. Now, as we move on, let me just mention the People's Republic of China has done spacewalks. They have not yet been involved in a manned maneuvering unit development, but there's certainly a possibility that they could. And as we look toward the future, the Orion spacecraft is being designed for missions to asteroids and bodies like the moons of Mars. And I think that we will find the need for maneuvering unit for getting around the microgravity environment of an asteroid. There certainly don't seem to be many handholds here. I don't think you can make footprints. I don't think you can walk on an asteroid. And it appears that a maneuvering unit would be the way to explore it and potentially to put a rope, a belt, or a cargo net around it and close it up so that it could be attached to or moored to an Orion spacecraft. I believe that the basic systems that we have developed in the MMU are adequate with the exception of the total delta V capability. We had 66 feet per second delta V, which is on the order of 60 kilometers or 55 kilometers per hour total. That is for starting, stopping, and for attitude control. We used cold gas compressed nitrogen, and I would hope that in the future we would perhaps utilize a warm gas system which uses something like hydrogen peroxide or another propellant to decompose into a temporary holding tank, a pressure tank, and then meters the gas out through the multiple thrusters. I don't think it's really feasible to have catalyst beds at every thruster when you have 24 thrusters on board, but certainly we need something with higher specific impulse. And I know that the Johnson Space Center is working on at least 2 concepts for maneuvering units at the current time. So, thank you very much. That concludes my remarks.
What wonderful presentation, Bruce. Thank you very much. If you don't know the next speaker, you haven't been paying attention. He's Soichi Noguchi, president of the Association of Space Explorers. But among the rest of us, he's just another spacewalker. He was selected by NASDA, the Japanese Space Agency, in 1996. Did some training in Star City before being assigned to STS-114 in 2001. It eventually flew in 2005, and a bit more about that later. He has been the chief of the JAXA, now NASA is called JAXA, astronaut corps since 2012. He's done 3 EVAs for over 20 hours. And when he was assigned to STS-114, it was a crew rotation flight. They were going to bring up Expedition 7, bring home Expedition 6. After the flight STS-113, Columbia was launched on STS-107. We all know what happened there. One of the biggest outcomes from a technical standpoint was to figure out, first of all, how to prevent the foam from coming off the external tank. But in the event that we couldn't 100% guarantee that that wouldn't happen, how could we repair any potential damage that might occur to the tiles as a result of that? So a lot of effort went into the TPS, Thermal Protection System, repair system, and Soichi will tell us a bit about that.
Well, thank you, LA. You stole my thunder, so not much to add, actually. Ladies and gentlemen, I'm humbled to be here amongst legendary spacewalker. I be just happy to share my experience. As LA obviously told that I was fortunate enough to do 3 EVAs back in 2005. And one of the EVA was pretty unique, so I want to share the story with you. My flight, STS-114, was called Return to Flight because of the fact that the shuttle must return to flight after the Columbia accident. Yeah, why do we have to do that? Kind of quick recap. 2003, January 16, STS-107, Columbia liftoff from Kennedy Space Center. And during the powered flight, part of the thermal protection system, it's a foam, fell off from the big orange tank and hit the left wing, leading edge of the shuttle wing. And they created a big hole. And on the top right, during the re-entry, the hot plasma went inside the main structure of the left wing, basically melt down the big frame. See what happened. After the Columbia accident, there is a thorough investigation going on. If you want to check all the document, you can Google it. It's a CAIB report. Basically, the thermal protection system hit the leading edge, and we have to do something. Well, I must tell you that the root cause of Columbia accident is that there's a big hole in the leading edge of the shuttle wing, and we call it reinforced carbon. That time, there's a lot of idea, a lot of testing going on in case we have the similar accident happens on the subsequent shuttle flight. And we tried very hard. We tried a lot of different options, but I must tell you that the repair of the RCC didn't work out well. And if this happens on a subsequent flight, our option is actually go to space station and abandon the space shuttle and use the Russian spacecraft, Soyuz. But one thing we can do is there was also a lot of incident pre-Columbia that the thermal protection system of the tile underneath of the space shuttle quite often had a lot of damage. This is a picture of a STS-27, I believe it's like a 1990. And post-flight, we found lots of damage on the back side of the space shuttle. And well, obviously the STS-27 survived this re-entry heat and came back to ground. But during this accident, the investigation team, both the RCC and this tile damage were highly investigated. And at least in order for us to return to flight, in order for the shuttle to return to flight, we have to have a countermeasure to fix this tile damage. And that's what we did back in 2004. And how we did it. This is actually ground testing. We have a lot of engineering support, both from NASA and also outside NASA, to find a way to cure the thermal protection tile in space. And eventually we created a new tool called the Cure in Place Applicator Assembly, or we just call it the GUGAN. And this, well, first of all, it has to work in 0G and in the vacuum space. And plus, you have to cure. Otherwise, during the entry, if it's vaporized, it's nothing else. So you have to cure like 24 hours or up to 72 hours in space, zero gravity, low temperature, and safe enough for shuttle to come back. That was a challenge on the engineering side. Another challenge was once you fill the gap with those goo type material, and after curing, it shall not protrude the outer line. We call it the outer mold line, more than 0.25 inch. It's like 6 millimeters. Otherwise, it creates a new bump on the very flat surface of a space shuttle. If it has a big bump, then on the back side of the wake, then the total temperature rise and probably create a significant damage to the tower system anyway. So it must be cured in 0G. It must be cured fairly flat. You can see there's a new tool. We just use a scale and just make it flat and see how it goes after 24 hours. So it doesn't, during this curing process, it doesn't rise up. So obviously the Bruce, I was just watching his presentation. He was more like a Formula One driver. And to me, I was just a road service of the space shuttle. Okay, and before we go up, we did a lot of testing using the 0G parabolic flight and make sure those curing place applicator, GUGAN, works in at least in zero gravity. We cannot test the high. We did the high vacuum testing as well, but we spend a lot of time in this parabolic flight, make sure those goo doesn't float out, and number two, it's walkable, means that the astronaut can manipulate those GUGANs in zero gravity. Okay, and I wonder if you can run the video possibly, and this is the result of our space flight. Okay, so this is, I believe, flight day 5. My crewmate, Stevie Ray Robinson, is getting ready for the first space flight. I'm getting in. And Andy Thomas was our IV, intervehicular crewmate, giving bunk. And suit up. This is a space shuttle airlock, slightly, it should be the same size as the International Space Station airlock. this just give you the, we did a lot of underwater testing as well. We cannot use the goo gun underneath the water, but at least do a lot of coordination because we have to use the robotic arm to get into particular location. There's no handrail, there's no, or the handling aids to get to the backside. And during the spacewalk, the first spacewalk, there's a lot of sample of a damaged tile on the back side, aft side of the space shuttle cargo bay. And we pull out those cure in place, basically handheld goo gun to repair, simulate the repair of the tile. And which was, it is not the real damage. The ground team pre-flight created a couple different pattern of the grooves, and all we do is open up the sample and repair it in space. And this is one example of the repair gun. And actually, the third spacewalk, well, this is still the repairing technique. Okay, yeah, that's good. So obviously, the tire repair experiment went very smoothly. And the actual issue with our flight was not related to the tile damage, but there's a very thin material in between the tile. We call it the gap filler. And during the ascent, we found that one of the very small piece of those gap fillers sticks out from the tile. And as I told you earlier, if there's some material sticks out from the flat surface, that will create the bump in the flat surface, create a higher temperature. So the actual repair happens that we go up to the backside of the space shuttle anyway, and just remove those small gap filler. So that was the end of my story. Thank you very much for attention.
Thank you, Soichi. Final speaker is Colonel Carl Waltz, retired from the United States Air Force, physicist by training, became a flight test engineer, spent most of his flying career in F-16s and airplanes we can't talk about, at least I don't know about them. He was selected to be an astronaut in 1990. He flew on 4 missions, 3 of them on the space shuttle, actually 4 of them on the space shuttle, because his 4th, which was to and from the ISS, or on the ISS for long duration, where he went to and from on the shuttle. So unusual in that he's one of the few people that has flown all 4 orbiters. He's also one of the few that has done spacewalks in both the Orlan suit and the EMU. He did 3 spacewalks total. One of the rare people to do a spacewalk on his first flight before we started the ISS assembly. That was in STS-51, and then did 2 more on his long-duration flight, again, 1 in the Orlan. So 3 EVAs, 18 hours, almost 19 hours, and he's going to talk not only about that experience, but about what's in the future, at least a potential future for spacewalking. Carl.
And thank you, Ale, and good afternoon, and thank you very much for being here and listening about EVA. It's one of the I guess, so I was inspired. I was a post, born just slightly before Sputnik, but I was captivated by the space program, and from the earliest times, I hoped to become an astronaut, and I was very fortunate to hit that time when there were a lot of astronauts flying on the space shuttle, and I applied 4 times and finally was selected. So it's one of those things where if you have a dream, always pursue it. Don't ever let go of your dreams. And so, but what I'd like to do is to talk a little bit about the future of spacesuits. I was very fortunate, as LA said, to have done, used both. Excuse me. To have done both an EMU EVA and an Orlan EVA, and we had about a month between those, and so so the experience of using both systems was very fresh, and of course I went through the training both for the US EMU and then also for the Orlan, and so I saw both training flows as well, and so as I looked toward the future, once I left the astronaut office, the active duty flyers, I went to NASA headquarters, and one of the responsibilities that I had was for new spacesuits. And so I'll show you some pictures of some prototype spacesuits, actually pressure garments, because the whole spacesuit, of course, is the pressure garment and a life support system in the current suits. In the future suits, they add an additional subsystem, which is provides the computers, the communications, what's called the informatics, to provide information to the crew member about the status of the suit, the status of the EVA, the status of your buddy, and also any other EVA players that might be robots, either on the surface of a planet or potentially flying around during an EVA. So let's see. What's that? Oh, okay, there we go. So just a little bit, you know, we've talked about U.S. spacesuits in the past, Ed White's EVA, the Apollo missions on a planetary surface, and then the EMU there, and I include the EMU in a past suit because this was the early versions of the EMU. The EMU that we fly on board the ISS right now has been significantly modified. New radios, new capabilities for longer stays in space. And then the present, of course, is the EMU on board the ISS right now. There's a picture of Tom Jones there. So is Tom around? So Tom was involved in some of the EVAs for the assembly, and then of course assembly on the truss there of the space station. And so that first EVA that I did was to try to begin the build-up, the preparation for the wall of EVAs that we knew was coming when we designed the space station, and so all that preparation turned out to be very successful, and that the by and large the assembly of the space station went really well. So as we look to the future, we need to figure out exactly what that future will hold for us, and so I don't work for NASA anymore, so I pulled this off of the internet. For future human exploration, and as NASA's journey to Mars, where we are right now is the Earth-reliant phase. So the space station, missions of 6 to 12 months with a return to Earth measured in hours. And of course, where we want to go is to Mars or the Mars vicinity. So mission 2 to 3 years. I hope we can do it faster. And then return to Earth measured in months. And of course, a lot of infrastructure required there. And of course, we're in the process of developing some of those capabilities right now. So the next destination is this proving ground area. And I think the feeling is, from a spacesuit perspective, that we probably need something a little bit different than what we have right now. The EMU has been in existence for about 40 years, and this is on the U.S. side. And so the proving ground, though, missions 1 to 12 months. The return to Earth is in days, and central to that, is the moon, and whether it's in cislunar space, connected with retrieving samples from an asteroid, or potentially low lunar orbit, and then going back to the surface for a planetary EVA. We don't exactly know that, but as we design new suits, we have to take all those into consideration. So as we look at what we might need for new spacesuits, there are some defining questions. That would be your level 0 requirements. And first and foremost is, what is the destination? So as we approach designs of a new suit, you really have to look at a systems engineering approach, and it starts with the destination. And is it a microgravity suit or a low gravity suit? Is it a planetary surface, or do you need a suit that can handle both? And if so, then you need to make sure you build in those capabilities for extensibility so that it can do a multi-mission job for you. In addition, you have to know what the host spacecraft is. For a number of reasons, what's your life support interface? Is it going to be a sea level environment like the space station with 20% of oxygen, or will it be something modified with more oxygen and potentially a lower starting pressure, so that it can affect how much pre-breathe you have to do. The other thing is mechanical interfaces. Will you use a suit port? That's been talked about a lot. Or will you use some sort of a min-volume airlock? Will you be coming out of a lander, for example? And there are some other interfaces, an electrical interface. You may need a vacuum interface for your suit if you have certain life support capabilities. And then also a computer interface, because with this new informatics age, you want to be able to download the most current information about the EVA that you're going to do. You want to make sure that you have all the up-to-date procedures, and so you can call those up to a heads-up display perhaps, and see those things right in front of your eyes as you're moving forward. Mobility requirements, again, will you be floating? Will you need some sort of manned maneuvering unit? Or will you be on a planetary surface? And if you're on a surface, will you be walking most of the time? Will you be riding? Or will you be doing a little bit of both? What size suits? What size are your crew members? What we found is on the EMU, it's very difficult to fit small crew members. And so what we want to try to do is build suits that can handle a larger range of size crew members to fit some of the smaller female astronauts as well as some of the bigger male astronauts. Make sure we can cover the waterfront there. Logistics. One of the things that's really important is how you resupply your spacesuit. And one of those things that I really liked about the Orlan is the care that was taken to develop the entire logistic train. And so the spacesuit just worked really well with an orbiting complex like we had on board the space station. And so the logistics plan, it was very straightforward, very simple, and it worked really well. And then a maintenance plan. These missions, going to the proving ground will be, from 1 year, from 1 month to 12 months. Once we get to Mars, there'll be, 2-3 years. Those suits may be going ahead of time, so you may have to catch up to your spacesuit when you get to Mars if you're going on a fast transport and your suits go on the slow boat. And so you have to know how to maintain those suits to make sure they'll function for you once you get to the destination and then for subsequent missions. So it's a tall order to develop the new spacesuit. So NASA has been looking at technology development. Back when I was at NASA headquarters, we were performing yearly test campaigns. Actually, A headquarters guy wasn't doing that. The people at Johnson Space Center and all the NASA centers were participating in this, and I just went and enjoyed the show. But we performed these yearly test campaigns in the western U.S. They were called the Desert Rats, and the plan there was to look at concept suits. And in general, these are the pressure garment part. The life support systems really weren't representative of what you'd need for a spacesuit. And we were starting to look at some of the informatics during these as well. And so this picture was taken in Flagstaff, Arizona. You can see the big mountains there with the pine trees. You wouldn't see the pine trees on a lunar surface. And then behind the two suits, you see a representative experiment similar to what the Apollo surface experiments, and we were trying to see how well we could deploy those with these new suits. And the two suits that you see up there, this is called the Mark III, and it's primarily a hard suit, so that it has a hard brief, hard upper torso, has this steel waist ring that provided rotation around the waist. So it's a big suit, heavy suit. Of course, it has these boots for walking. And then this suit is called the I suit. It was developed by ILC Dover, and of course funded by NASA. Characteristics of both these suits, they're rear entry, similar to the Orlan, so that you don't have to wiggle in through the middle like we do with the EMU right now. And the I suit was all fabric, and so none of the heavy-duty composites that were in the Mark III suit. So it turns out that for the pressure garments, that's the fundamental discriminator, is whether it's a hard torso or whether it's a soft torso. And here's just another view of that Mark III. It has that hard upper torso, hard brief, rear entry, walking boots, and then we tested it during Desert Rats. And so this is a view of that Desert Rats. And so what you can see, of course, you have that Mark III suit with the astronaut test subject. You also have a rover. And so one of the things we've looked at is different rover versions and how that suit then interfaces with the rover. But the other thing you see is a number of different surface robots. And so, one of the concepts would be to have robot helpers along with the suited astronauts. And so the astronauts will have to have a means of communicating and gathering data from those robots as well. Hence the need for a very capable system of communications and data display. Here's another view of the I suit. Mike Foale and I had a chance to drive from headquarters in Washington, D.C. up to ILC Dover. And what we found is that the suit was very comfortable when we put it on. They had us go through a little mobility test here to look at range of motion. They had this little four-wheel ATV, and we both got on with the pressurized suit. There's another exercise, climbing a ladder, that was very easy to do in the I suit. And so we found from a mobility standpoint, this I suit was very easy to walk in and work in. And I think the concerns in the EVA community have been, is it durable enough for EVAs on, say, a planetary surface with a lot of sharp objects. So NASA, through the Advanced EVA system, the AES program, has been developing a number of spacesuits, pressure garments, as well as life support systems under that AES program. It's being directed by the NASA engineering group there at JSC and involves a number of centers and industry. And so they have taken the Mark III a little bit further to the, this is the Z1 suit, and this is in a zero-G airplane. They're looking at some aspects of the suit there. They also looked at decorating the suit for, I think it was part of a campaign. But it is a rear entry, hard upper torso, and waist brief. It features an elliptical helmet now and an improved shoulder joint to improve mobility in the shoulders and also to prevent injury. And then the AES program is planning on a Z2 suit, which will be coming out shortly. It's being developed right now at ILC Dover. But these are pressure garments. And again, the life support system technology is being developed in parallel, as is the informatics. And then, in addition, there's an industry-led program led by Oceaneering, and I'm an Oceaneering guy right now, so I get to play with this suit as well. But it's part of it was part of the Constellation program, and this is the Constellation spacesuit system. We're doing risk reduction on EVA technologies, and so we're also developing a prototype pressure garment as well to improve fit, comfort, mobility, and safety, supporting multiple pressures, as will the Z suits, rear entry, and the desire is to figure out a way to reduce mass to orbit, because every pound you take or every kilogram you take costs a lot of propellant to get that system to the destination. And so right now the testing is ongoing at the Oceaneering Space Systems facility, and we've also developed a new liquid thermal garment that is featured both in this suit and the suit, the Z2 suit. You can see this pressure or this liquid thermal garment here. Basically, the liquid cooling garment that is used in the EMU is basically the same design that was used during the Apollo program. And so the engineers at Oceaneering have worked to improve that design, to target muscles, to improve the garment itself so it actually feels good to put on and wear, and it weighs about half of what the current LCVG weighs, and provides superior performance. And then we're also looking at how the suit might be based on the ISS. NASA asked us to look at that, so we've developed a concept of operations for how we would operate that suit. So the pictures of the suit should be coming out very soon. We're waiting to have a media unveiling, and we're working with NASA on that. So watch the space news outlets, and it'll be out there shortly. So really, I think that's all that I had to say. I think that one of the important things that we need to look at is how we continue to explore and how we can design new suits that'll help us facilitate our exploration. So thank you very much.